This video is designed to be watched after you've already studied extrema and also Lagrange multipliers. So the first thing I want to mention here is that when we're talking about extrema for functions of two variables, in other words 3D surfaces, there is a comparison we can make to Calc 1, where we are studying functions of one variable. So for example, if I'm looking at a function such as this, well, when we take a look at the potential relative extrema, that would occur at these peaks and valleys. So these are our relative extrema. Now, when we are looking for those in Calc 1, of course, we are taking a look at when is the first derivative equal to 0 or undefined, are also places where we can have extreme values occurring. So to continue with this, let's just mention that while these are all relative max values or local max values, the only one that is overall considered an absolute max is this top value, because absolute max means that it is the highest point for the entire function. Now, one thing to clarify here is that the absolute max could have occurred in more than one location. So really, it's the y value here that's the absolute max. It's not the coordinate pair. Now, let's compare that to the relative min. Again, we have two relative minima locations, which are these valleys. And notice that, however, since the arrows are going down forever on this function, there is not an absolute min. What if we, however, narrowed this function down? What if we said, well, we only really want to use the values between, say, this x value and, let's extend this out a little, how about this x value? And that will narrow us down to only this part of the function. So we have applied a constraint to this, and notice that now we actually do have an absolute min. So we get the absolute min for that sort of narrowed constraint function. You know, if we've constrained us to fewer x values, right? We're not going from negative infinity to positive infinity. And we still actually have the same absolute max. So what we do when we're looking for absolute max and min when we have a function of one variable is that we look on the boundary. In other words, we look at the end points, and we also look at any relative, or we should say maybe critical points, okay? Look at any critical points. And so what we do when we start looking at extrema for f of xy is that we, assuming that we have some sort of a constraint function, we are going to be taking a look at what that constraint function is telling us. And so, for example, if I have a constraint function like this, and let's suppose that my surface in this case is, I don't know, like a paraboloid. Then, you know, I've got this paraboloid going up here and on forever and ever, right? Well, when I say x squared plus y squared is less than or equal to 16, what I'm doing is I'm saying, well, suppose right in here this is x is 4, y is 4. So here's x is 4, here's y is 4. We have this circle, and we picture this basically like beam of light shooting up and down forever along this function. So you sort of almost picture like a flashlight beam for this, because it is this circular beam of light of radius 4 going up forever and down forever. And the question is now, within that beam of light, where is this function at its highest point and its lowest point? So I'm not going to dig into the details of this, but I'm going to mention that what we're leading into next is that we're really going to try to distinguish between the boundaries, which are like the endpoints for a function of one variable, and the interior, which would be where we would be looking for relative minima and maxima. So we would break something like this up into really two different questions, which is, what is the biggest value for my function, or the smallest value for my function, when we're at the boundary of that beam of light? And also, what if we're on the inside of that beam of light, strictly inside? And these are going to require different methods. And we're going to continue in the next video on the theme for this. This video is just kind of a little intro to like, how do we tie these concepts together? But the main thing I want you to understand is that there is a really big difference between looking for where is a potential absolute min or max on a equality constraint, right? Something like a circle. This would also be something where we look at it differently. If it's a constraint would be part of the boundary, might be a line. And then this is more of a region. So this is a boundary curve or a line, right? And this is an interior region. And the overall theme is that the interior region, we would be looking at the information when we looked at partial derivatives. Not necessarily needing to go so far as to apply the second partials test and try to figure out what's a relative max, what's a relative min, what's a saddle point, but just identifying like what are those critical values that are actually on the interior of the region. Because if there's a critical value for my function outside of the region in question, I don't care about it for this particular topic. So we'll be looking at partial derivatives for the interior of the region, and then our top candidate for what we do on the boundary is going to be Lagrange's theorem. And so that boundary is when we have the equality. So again, it helps to tie this back in. We are looking now in this particular topic, we are looking for the absolute extrema for a function that is in 3D. And so we are going to be looking at different sorts of constraints. Some of them are going to be strictly equations, in which case we would use Lagrange. Some of them are going to be strictly inequalities, in which case we will use partial derivatives. And some of them will be both, in which case we have to do multiple methods in order to find the possible high and low points. And then in the end, just like when we found all the candidates for points where things might be at the biggest or smallest, we're going to plug those things back into the function and see which is the biggest and which is the smallest output value.